A world built entirely from collisions should have stayed an ocean of fire, forever. This one didn't. So where did all that heat go? This ocean of rock is Earth, newly formed. Two things built it: falling rubble, crashing together for millions of years, and one giant blow, the collision that made the moon. Both crashes turned into heat, enough heat to melt rock all the way down to where the core will form. Scientists call this a magma ocean. It should behave like any hot thing, cool down and stay cooled. And it does cool by radiating heat into space, exactly like a campfire once you stop feeding it wood. Every second, this world glowed a little less bright, a little cooler, into the dark. A bare ball of magma this size should freeze solid within about 1,000 years. On Earth's own calendar, that is over before the day even ticks. But something wrapped around this planet and slowed it down. Scientists call it a greenhouse blanket, a thick shroud of steam and carbon dioxide, breathed out by the melting rock itself. Trap the heat instead of losing it, and cooling stops being quick. Models suggest the whole ocean took tens of millions of years to fully freeze. A few days on Earth's calendar, not hours. Eventually, the surface cooled enough for that steam to fall, as rain instead of rising as vapor. The rain that followed became Earth's first ocean, and under it, the melted rock had begun doing something new, freezing into patches of solid crust, the planet's first skin. So is Earth solid now, all the way through? No. Deep down, part of it is still liquid rock today, 4.5 billion years later. Here's why. Rock itself makes heat. Traces of uranium, thorium, and potassium are decaying inside the mantle, slowly, and every decay lets out a little warmth. Scientists call this radiogenic heat, heat made by the rock's own radioactivity, not left over from any collision. Spread through the whole mantle, that heat is tiny. Each chunk of rock makes less warmth than your own body does, pound for pound. But there is an enormous amount of rock. We can see the liquid layer it keeps alive without ever drilling down to it. Every big earthquake rings the earth like a bell. The echoes draw a picture of what's down there. Solid rock, then a molten layer, deep below our feet. Why did some worlds end up differently? Size decides it. A smaller world has more surface for its size, more skin to lose heat through, less body to hold it. The moon is about 1/4 of Earth's width. It finished cooling long ago. No volcanoes now, no magnetic field, stone cold and still. Mars is about half of Earth's width, in between. Its core cooled enough to shut off its magnetic shield around 4 billion years ago. But a little warmth still stirs deep inside it today. Earth is the biggest rocky world there is, big enough and radioactive enough to keep an engine running underneath its skin, 4.5 billion years on. So the world that should have stayed an ocean of fire did cool, exactly as much as its size and its own radioactivity allowed. Enough to grow a crust an ocean could rest on, not enough to go cold all the way through. A world built entirely from collisions should have stayed an ocean of fire, forever. This one grew a skin instead. On Earth's calendar, that took until January the 11th, 4.41 billion years ago. And deep down, it is warm still. Next time, straight down. Under your feet, everything heavy is still sinking toward the middle, and it is taking the gold with it. Earth's first ages are a long story, and this was one chapter of it. The rest of the arc is on the playlist, Birth of a Planet.